Okay, this section is about randomness. So I'm talking about randomness, and here's a very short introduction. Randomness exists in nature. Different kind of randomness is chaotic or some intrinsic randomness like quantum randomness. Based on different kind of randomness, we have different kind of randomness, random number generator. For some application, the random number generator that generate uniform distributed random numbers are enough. But for other applications, for secure applications, we need intrinsic random number that is unpredictable to anyone, unpredictable to Eve. So the quantum random number generator is a very good inherent random and cannot predict by eavesdropper. However, the real device may have imperfections. The components in the devices may deviating during time, so eavesdropper may attack the real device to obtain the random number or even to manipulating the random number that generated. So one method is to real-time monitor the device and do proper shielding to make sure the generator performs as well what we expected. But this is not that practical. So another method is to develop theory. Okay, I'm working on experiment, so I'm just talking about the DIQRNG, which is the highest security level in device independent random number generation. The device can be seen as a black box. The user just input the random basis, and the device output the random number. With only the input and output random numbers, the user can certify if the device working properly and how much randomness can be extracted from the device. So this is the quantum random number generator. It's also called self-testing QRNG. The requirement of this kind of random number generator should not depend on the some assumption like IDs. It should be most general assumptions and should consider the most general attacks or maybe set information between the device and the eavesdropper. And the device should generate random bits that is not vanishing and should be efficient. It's about 2016, the entropy accumulation theorem solved all the problem, and it's now the highest level of the device-independent random number generation theory. Since the theory is always based on bioinequality violation, especially it's based on some loophole-free bioinequality violation, so the experimental request is very high. The experiment requires very high system efficiency to make sure there's no detection loophole, and there's another requirement for the no communication between the measurement stations or the measurement station and the source. This can be done with the space-like separation between the different locations, or it is possible to do proper shielding. Recently, there are a few experiments on the QRNG. One experiment is based on the loophole-free bioinequality test this year against the classical adversary, and we did another experiment last year with just closing detection loophole, but now the locate loophole, and now we are working on both loopholes. And very recently, we see an article report on randomness extraction with continuous down conversion source, and I think this is the next talk. So I will review the theory very briefly since I'm working on experiment. In the DIQRNG experiment, normally there's a generation trio and a test trio with a very small probability. We choose the test trio with the basis X and Y to choose the basis for the entangled pair measurement, and for the generation trio, we should choose fixed basis for generation of the random number. In our experiment, we set all the terms to be the test trio, so it is a randomness expansion. So for each trio, we calculate a such value, and this is a GM. And for all the n trios, we can calculate an average CHS violation. the G bar. With this violation in hand, we can calculate the entropy accumulated during the whole experimental trials. And with this entropy, we can extract at least H epsilon minus TE real numbers. So here T is the failure probability for the extractor. So the details can be found in the entropy accumulation theorem. And here is just the functions. And next, we'll talk about our experiment a bit in detail. Our experiment is based on loop-free Bell-inequality test. And the setup is looking like this. We did the experiment in 3 locations. In the middle is the source, and the opposite positions is the measurement position, as in above, that is about 93 meters and 90 meters away. Let's start from the middle. We use a gain switch laser. It's a pulse laser at the seed, which is then amplified and up converted to 780 nanometers. As a pump light for the entanglement source. The pump light is then polarization modulated to inject to the second loop for entanglement pair generation for the quantum state we design. And then we couple the entanglement pairs with to a single fiber to distribute the photon pairs to the measurement stations. At the measurement station, we again couple the light into free space and modulate between the 2 bases using a pixel, and then we measure with replace and PBS and couple back into single fiber for detection using high efficiency single photon detectors. So the most important problem in the experiment is about the efficiency. We need very high efficiency to achieve a violation without any detection assumption. So we use very high specific coating for the mirrors and wave plates, both in the source and the measurement station. We designed mode coupling in the source. That is, we designed the beam width of the pump source and the entanglement collection width to make sure the collection efficiency of the entanglement pair source is the highest. We also made a similar calculation for the measurement station. We coupled the light from signal fiber to free space and back into the signal fiber. So we designed the coupling efficiency to be the highest. We select the wavelength of the entanglement pair to be 15-16 nanometer, so we can transmit the photons from the source to the measurement station with almost, I think, 99% efficiency, and we developed very high efficiency single photon detector to make sure the efficiency is okay. So here are the efficiencies for our system. In our source, we achieve about 94% efficiency, maybe a bit higher because we measure the other efficiency with conservative method. And the optics is about 96%. Here, the single photon detector, the efficiency is about 92%. So without the efficiency, we can actually we measure the system efficiency, the Herodian efficiency, to be more than 78%, which is high enough for Bell violation. And with this efficiency and with the visibility of our system, we optimize the quantum state and the measurement basis in the system is okay, it's just there. We measure our quantum state with tomography, and the state fidelity is measured about 99%. The next thing is about the spatial separation. We use this spatial separation to guarantee there's no communication between the measurement station, the measurement event and in one station, and the measurement event in another station, and also the event of the entanglement creation and the measurement setting choice. So with this equations there, we design the distance between the experimental locations and the delay of the different events to make sure all these equations are fulfilled. So with efficiency and the location design, we can validate the Bell inequality with that loop-free method. The next thing we do is to optimize the intensity of each pulse. So it's our source is a pulse pulsar cells with a frequency about 200 kilohertz. We optimize the photon intensity, the internal pair intensity in each pulse. This is because if the mean photon number is too small, most of the trails are in vacuum. And vacuum pulses do not contribute to our Bell violation. But if the mean photon number is too large, multiphoton effect may dominate, and multiphoton will contribute negatively to the Bell violation. So there can be a optimized value. We tested the optimized value in experiment, and we also modeled the multiphoton pair effect in theory up to the three photon pairs. We consider all the possible cases, and then we optimize the value to be about 0.11. In the experiment, we conservatively selected 0.07 as the mean photon number to test the Bell inequality and to generate the random number. After we get the raw base, we need to extract the final random number using top-list matrix. We used the FFT method to accelerate the multiplication of top-list matrix. Actually, we used a grouped FFT acceleration. This is not the optimized method as the original FFT and the convolution, but this method saves memory, so we can run our algorithm in a personal computer in 11 hours. So the matrix is about 137 gigabits times maybe 62 megabits. This is the final random number. So here is a very brief result about our experiment. We did the experiment in about 96 hours, which is about 6.9 times 10 to the 10 experimental trails. We get an average violation about 2.7 times 10 to the minus 4. We monitor here the CHSH violation in the experiment. It's rather stable with a few manually adjustment of the experiment. We get about 62 megabits random number in finally, and which is about 180 bits per second with a uniformity within 10 to the minus 5. Actually, the result is about 57% of the asymptotic case. And actually, we have got random number since about 10, maybe less than 20 hours. But we did it 100 to 100 hours to perform the needs uniformity test. Our final random number passes all the uniformity tests. But of course, the randomness is coming from the quantum mechanics, not from the uniformity test. Besides, we did a hypothesis test of local realism. The no hypothesis there is the experimental result examined by the local realism. And here we characterize the result with the p-value. We use the PBR method to outbound the p-value without some IID assumption. The result is a very small p-value here, indicates strongly reject of local hidden variable. And we also did a hyperfast test of no signaling. The result tells us there's no evidence of anomalous signaling. And here's a very short outlook to the next step. Bubbles is to do the full random number expansion and hopefully amplification. And next, we are looking for different kinds of device-independent protocols that can be done in our experiment setup. And we acknowledge the colleagues in our university for the experiment in Tsinghua University and NTT for the theory assistance and for in CMIT for the development of the superconducting nanowire synchrophoton detector. We acknowledge the National Key Research Development Program of China, NSFC and CS for the funding. And thank you.
Thank you very much. We have time for questions.
So in excuse me, in your outlook, you say one of the things you want to do is full device-independent randomness generation. What expansion? Sorry, what is the extra thing that you need to do that? Why does your experiment not already do that?
Thank you. The question is about what is a full random number expansion and what we did, the difference. So what we did now is we can call it a simulation or maybe test of the randomness expansion or the test of random number expansion because we did all the test trail in the experiment. And the next step we need to do is we need to input some short number or random number into the system, and the system can generate more and more and more random numbers output. For now, we have the randomness input the system, and we get some more randomness output, but not more random numbers. In the next step, we need to generate more numbers. So
the problem is that the output randomness may be correlated with the input randomness.
No, I don't think it's a correlation. It's because we, for now, the input random number is more than the output random number. Because for each trail, we put in a random number, and we get less than 1 bit of random number. But this is because we test all the test trail here in the experiment. Next, we will use a unbalanced scenario, and we have maybe a small bit of ones and a large amount of zeros, so we can generate more random numbers output from the system.
That's what you want to do next?
That is the next step.
Okay.
Any other questions?
For a lot of applications of random numbers, you want the user to trust you. So this device-independent scenario is a little bit like a zero-knowledge proof. It convinces you that the random numbers are good. But if you're running a lottery, it doesn't convince the customers who buy the lottery tickets that the random numbers are fresh. They could be old ones, unless the customers who buy the lottery tickets also participate in feeding input into the Bell measurements, which is pretty impractical. So I think this is a general weakness of device independence in terms of the, let's say, the commercial uses of random numbers, because the main problem is not that nature is fooling you, but that you are fooling your customers.
Okay, thank you for your question. And I think I may need to do some note here, because here we are doing some, I think it's some short note here. This is all the assumptions in our experiment or in the theory, and for such kind of DIQRNG, I think if the customer or the user has the ability to trust some small amount of random number himself, and then he puts the random number into the system, it should be okay to test.
Assume that A and B's devices are in a secure lab. That's an impractical assumption, that devices cannot communicate through a covert channel. So that's the problem with trusting that assumption.
Yeah, I see, thank you. And actually, in the future, the device should not be that large as now. It should be actually in a room, so the user can secure one room. It's okay. Because the time requirement for now is a bit higher, so the distance should be 100 meters. But in the future, it's maybe, for example, 1 meter is okay.
Yeah, the producer can trust the numbers, but the user can't trust the producer.
Yes, you're right. So, yeah, we can discuss it. Yeah.
Maybe last question. If no question, please thank the speaker again.